Welcome to Artificial Intelligence Incorporating High Dimensional Statistics, PhDAI 730 Lecture 11. This is your Professor Atif Reed Muhammad. We will delve into the complexities and innovative techniques of high dimensional statistics, a field that has become increasingly important in the era of big data. As datasets grow, not only in the size but also in complexity, the challenge of dealing with a large number of variables, many of which may be irrelevant or redundant, becomes more pronounced. High dimensional statistics address these challenges by providing the tools and methodologies necessary to analyze data where the numbers of variables can exceed the number of observations. By focusing on the concept of sparsity, we can identify and concentrate on the most relevant features, thereby simplifying the data and making it more manageable. So, high dimensional statistics represents a fundamental shift in how we think about data analysis. Traditional statistical methods were developed in an era when collecting data was expensive and time consuming. So researchers typically had many more observations and variables to study. However, modern technology has reversed this relationship. Today, a single medical scan can generate thousands of measurements. A genomic test can assess millions of genetic markers, and a financial transaction can be characterized by hundreds of features. This abundance of variables relative to observations breaks the mathematical foundation upon which classical statistics was built, necessitating entirely new theoretical framework and practical methods. The challenge goes beyond more computation. When we have more variables than observations, traditional methods like ordinary least square regression produce infinitely many perfect solutions, making it impossible to choose among them without additional assumptions. Moreover, the curse of dimensionality means that as we add more variables, our data becomes increasingly sparse in the high dimensional space, and our intuitions from 2 or 3 dimensions fail dramatically. High dimensional statistics address these challenges by introducing structural assumptions, most notably sparsity, that reflects the reality that in many applications only a small fractions of the measured variables truly matter for the phenomenon we are studying in this specific time. The curse of dimensionality refers to various phenomena that arises when analyzing data in high dimensional spaces, including exponential growth in volume, sparsity of data points, and breaking down the geometric intuition from lower dimensions. So imagine a square with side length 1. If you inscribe a circle inside it, the circle occupies about 79% of the square's area. Now move to 3 dimensions. A sphere inside a unit cube occupies about 52% of the volume. By the time you reach 10 dimensions, the hypersphere occupies less than 0.25% of the hypercube volume. This means that in high dimensions, almost all of the space is concentrated in the corners far from the center for practical data analysis. This implies that sample points become increasingly isolated, making it difficult to find nearby neighbors or estimate local properties of the data. This phenomenon has profound implications for machine learning algorithms, methods that rely on distance calculations like k nearest neighbors or kernel smoothing struggle because the notion of nearness loses meaning when all points are approximately equidistant. Classification boundaries that seem clear in two dimensions become ambiguous in high dimensions because there is so much empty space. Even more surprising, random vectors in high dimensions tend to be nearly orthogonal to each other, meaning that correlations between variables can be difficult to detect reliably. Understanding and mitigating the curse of dimensionality is therefore essential for developing methods that work effectively with modern datasets. The sparsity principle is both a blessing and an assumption that enables high dimensional statistics to work in practice. It reflects an empirical observation across many domains. While we might measure thousands of variables, often only a handful truly drive the outcome we care about. In genomics, despite having 20,000 genes, a particular disease might be primarily influenced by mutations in just 5 or 10 genes. In text analysis, while documents might contain thousands of unique words, sentiment might be determined by a few dozen key terms. This principle transforms an impossible problem, estimating thousands of parameters from hundreds of observations, into a tractable one, finding which few parameters are non-zero and estimating only those. However, sparsity is an assumption, not a guarantee, and its validity varies across applications. In some domains, like image processing, sparsity might not hold in the raw pixel space but emerges after transformation, like wavelet decomposition. In others, like climate modeling, effect, effects might be genuinely distributed across many variables rather than concentrated in a few. The art of high dimensional statistics involves not just applying sparse methods blindly, but understanding when sparsity assumptions are reasonable. What sparse means in different contexts. Is 10 variables out of 1,000 sparse? What about 100 out of 10,000? And developing methods that degrade gracefully when sparsity assumptions are violated rather than failing catastrophically. So, under what conditions we can guarantee that sparse recovery algorithms correctly identify the true support set of relevant variables, and how does depend on correlation structure among predictors? That's a research question. You can conduct a study on top of it. L1 regularization is also known as lasso regression. Lasso revolutionized high dimensional statistics when it was introduced by Robert Tibishirani in 1996 because it elegantly solved two problems simultaneously: regularization and variable selection. Unlike ridge regression, which shrinks all coefficients towards zero but keeps them all in the model, Lasso's use of the L1 penalty, sum of absolute values, has a geometric property that pushes coefficients exactly to zero. This happens because the L1 constraint region has corners, and when the elliptical contours of the least squares objective intersect this diamond shaped region, they often hit the corners where some coordinates are zero. This automatic variable selection makes lasso outputs far more interpretable than dense models with thousands of tiny coefficients. The practical impact of lasso extends beyond statistics into machine learning, signal processing, and virtually every field dealing with high dimensional data. Its computational efficiency, solvable via coordinate descent in times comparable to ordinary least square, made it practical for real world applications. However, lasso is not without limitations. When predictors are highly correlated, lasso trends to arbitrarily select one and ignore others, which can be unstable and problematic for interpretation. The method also introduces bias in coefficient estimates, particularly for large true effects. These limitations have inspired numerous extensions and refinements, including adaptive lasso, elastic net, and debiased lasso, each addressing specific shortcomings while preserving the core appeal of simultaneous shrinking or shrinkage and selection. The research question is, how can we extend Lasso's theory to handle highly correlated predictor groups while maintaining both statistical consistency and computational tractability in ultra high dimensional regimes? So, in pharmaceutical research predicting drug efficacy from molecular descriptors, Lasso automatically selects the 20 most relevant chemical properties from 5,000 candidates, reducing experimental costs and improving interpretability. That's an example, a real life example. So L2 regularization is ridge regression developed by Arthur Horrell and Robert Kennard in 1970, predates Lasso, but remains equally important in the regularization toolkit. Its fundamental insight is that when predictors are highly correlated, the ordinary least square estimator has high variance. Small changes in the data lead to large changes in coefficient estimates. By adding a penalty proportional to the sum of squared coefficients, ridge regression trades a small amount of bias for a large reduction in variance, improving overall prediction accuracy. The mathematical beauty of ridge regression lies in its closed form solution. Simply add a constant to the diagonal of the design matrix before inverting, which stabilizes what might otherwise be an ill-conditioned or singular matrix. The L2 penalty has different geometric implications than L1. So the portfolio optimization with hundreds of correlated assets uses ridge regression to stabilize weight estimates, preventing extreme positions that result from inverting near singular covariance matrix in mean variance optimization. So the research question here for you to conduct is, what is the optimal tuning parameter selection strategy for ridge regression when the goal shifts from prediction accuracy to causal inference in high dimensional observational studies? The elastic net regularization. So the elastic net emerged from recognizing that both lasso and ridge regression have complementary strengths and weaknesses. Lasso excels at variable selection but struggles with correlated predictors, often selecting one arbitrarily and ignoring others. Ridge regression handles correlation gracefully but does not perform variable selection, keeping all variables in the model. Elastic net, introduced by ZOU, and Hasty in 2005, combines both penalties. A mixer parameter, alpha, controls the balance between L1 when alpha is equal to 1 and L2 when alpha is equal to 0 penalties. This hybrid approach can select groups of correlated variables together while still maintaining overall sparsity in the model. The practical advantage becomes clear in applications like genomics, where genes often work in pathways with multiple correlated genes performing similar functions. So fMRI, brain imaging analysis, with correlated voxel activations, uses elastic net to identify brain regions associated with cognitive tasks, selecting representative voxels from each relevant cluster rather than arbitrary single voxels. The research question here for you to ponder upon and conduct study: can we develop adaptive elastic net variants that automatically learn the optimal mixing parameter between L1 and L2 penalties based on underlying correlation structure without cross validation? So I would strongly suggest you to look at Google Scholar or IEEE Explore to find some answers for your learning. Variable selection methods. Variable selection is one of the oldest problems in statistics, but high dimensionality adds new urgency and complexity. Classical stepwise selection methods, forward selection, backward elimination, or both, involve searching through possible models by iteratively adding or removing variables based on statistical criteria. So, modern variables selection methods take fundamentally different approaches. Lasso and related regularization methods perform selection through continuous optimization rather than discrete search. So, customer churn prediction models screen thousands of behavioral variables, website clicks, support calls, purchase patterns to identify the 30 or 40 leading indicators that warrant real-time monitoring and intervention. Again, a research question for you to look at is: how do we rigorously compare different variable selection procedures, stepwise lasso, knockoff, stability selection in terms of false discovery control and power across varying sparsity and correlation regimes? So that's a good way to look into. Principal component analysis. This is an area of its own, so I would suggest you to conduct a research on this. Here, PCA transforms high dimensional correlated variables into a smaller set of uncorrelated principal components ordered by variance explained, providing a low dimensional representation that captures maximum data variation. Image compression systems use PCA to represent high resolution images with thousands of pixels using only hundreds of principal components, reducing storage requirements by 90% while maintaining visual quality for most applications. So, in spiked covariance models, where signal eigenvalues are mixed with noise eigenvalues, what are the phase transition boundaries for consistent recovery of signal eigenspaces as dimensionality and sample size jointly increase? Now, that's a question that you can ponder upon. So, do use the Google Scholar or IEEE Explore. That'll give you a good idea how to work with the PCA or principal component analysis. Random projections. Random projections reduce dimensionality by linearly transforming data into a lower dimensional subspace using random matrix, approximately preserving distances between points according to the Johnson-Lindenstrauss lemma with high probability. Large-scale recommendation systems project user preference vectors from millions of items to thousands of dimensions using random projections, enabling fast similarity computations while maintaining recommendation quality. What are the minimal target dimensions required for random projections to preserve not just pairwise distance but higher order statistical structure like covariance matrices, moments, or manifold geometry? Google Scholar is your best friend to find the answers. Compressed sensing. So, compressed sensing revolutionized signal processing by demonstrating that sparsity can overcome the Nyquist-Shannon sampling theorem limitations. Traditionally, wisdom held that to reconstruct signal of bandwidth b, you must sample at rate 2b, so 2 as a number and b as the character. But if the signal is sparse, containing only k non-zero coefficients out of n possible compressed sensing shows you can recover it from merely OK log n. So capital O and a small bracket K log n. I suggest you to look into that as a random measurements that how it happens. So in real life, MRI scanning uses compressed sensing to reconstruct full images from incomplete case space measurements, reducing scan times from 45 minutes to 15 minutes. That is the artificial intelligence incorporation in the MRI scanning, while maintaining diagnostic quality, improving patient comfort and throughput. So, can we establish universal recovery guarantees for compressed sensing with structured sparsity block tree graph that account for both measurement noise and model specification in practical applications? Now, that's a good one for you to answer. High dimensional covariance estimation. High dimensional covariance estimation addresses the challenge that sample covariance matrix becomes singular and unstable when p is greater than n, requiring regularization techniques like shrinkage, banding, or thresholding to produce well-conditioned estimators. Risk management in finance requires estimating covariance matrices for portfolios with thousands of assets from limited historical data, using shrinkage estimators that blend sample covariance with structured targets. Under the sparsity or structural assumptions on the true covariance matrix can we achieve minimax optimal convergence rates, and how do optimal rates depend on matrix norms used for evaluation. Graphical models in high dimensions. Graphical models represent conditional independent structures among variables through graphs where edge presence indicates direct dependence in high dimensions. Sparsity assumptions on the graph structure enable learning from limited samples. So this is an area that I suggest you to put a little bit more research by yourself, as in high dimensions graphical model estimation become both more challenging and more valuable. With thousands of variables, a dense graph is uninterpretable and impractical, but sparse graphs with most edges absent become informative. They identify the key direct relationships. The graphical lasso algorithm, which adds L1 penalties to precision matrix estimation, has become standard for this task. So the gene regulatory network reconstruction identifies which genes directly regulate others from expression data, using sparse graphical model estimation to separate direct regulatory relationships from indirect correlations through intermediate genes. That's in gene therapy. So the research question for you is to ponder upon and check on Google Scholar. How can we develop scalable algorithms for learning time varying graphical models from streaming high dimensional data while providing theoretical guarantees on structural recovery under temporal smoothness constraints? So that's a good question for you to ponder upon. Multiple testing problem. Multiple sensing. Um, it's technically multiple testing. And also sensing is the area that I would suggest you look at. Addresses the inflection or inflation. It can be inflection point in multiple sensing, whereas multiple testing addresses the inflation of false discoveries when conducting thousands of simultaneous hypothesis tests, requiring procedures that control family-wise error rate or false discovery rates across the entire testing family. Genome-wide association studies test millions of genetic variants from disease association using FTR controlling procedures like Benjamini Hochberg to identify truly associated variants while limiting false positives to acceptable levels. What is the fundamental limit of multiple testing power under arbitrary dependence? Structures among tests satisfies And can we design adaptive procedures that approach this limit without knowing the dependence? False discovery rate, or FDR control, as we discussed earlier. False discovery rates is the expected proportion of false discoveries among all discoveries, providing a less conservative error criterion than family-wise error rate while offering meaningful control in high-dimensional exploratory analysis. So, proteomics experiments comparing protein abundance between disease and control groups apply FDR control to thousands of proteins, identifying differently or differentially expressed candidates while guaranteeing that fewer than 5% are likely false leads. How can we develop FDR procedures that maintain power under complex dependency structures while also providing valid inference on the false discovery proportion for finite samples rather than just asymptotic guarantees? Now, that's a question you can look into. Cross validation in high dimensions. The cross validation in high dimensions require careful implementation, as standard k-fold procedures can be overly optimistic due to information leakage, necessitating nested cross validation or alternatives like stability selection. Developing predictive models for customer lifetime value from hundreds of features uses nested cross validation, outer loops for performance estimation, inner loops for hyperparameter tuning to prevent overfitting and providing honest accuracy estimates. So, can we characterize the bias variance trade off of different cross validation schemes as both N and P grow? So and develop data-driven selection rules for choosing between leave one out, k-fold, and Monte Carlo approaches. Now that's a question that you can look into by conducting your research. Shore independent screening. Shore independent screening is a features screening method that ranks variables by marginal correlations with the response, rapidly reducing ultra high dimensional feature spaces to moderate dimensions while retaining all truly relevant variables with high probability. Text mining applications analyzing millions of n-grams for sentiment predictions using shore independence screening to reduce from 5 million features to 10,000 candidates in seconds before applying sophisticated selection methods. So the research question for you comes: under what design conditions does marginal screening maintain the shore screening property when predictors exhibit complex interactions, and how can we modify screening to detect pure interactions effects without maintaining main effects? Sparse principal component analysis. Sparse PCA modifies traditional PCA. Climate pattern analysis from thousands of weather station measurements uses sparse PCA to identify regional climate models, El Nino or monsoons, using only key station combinations, facilitating scientific interpretation and physical understanding. What are the fundamental statistical limits for simultaneously estimating sparse eigenvectors and their corresponding eigenvalues, especially in setting where the sparsity level itself is unknown and must be estimated? So minimax theory in high dimensions. Minimax theory establishes fundamental lower bounds on estimation and prediction errors achievable by any estimator over a specified function classes, characterizing what is statistically possible regardless of computational constraints. When evaluating new sparse regression algorithms, minimax rates provide benchmarks for assessing whether proposed methods achieve optimal performance or if further improvements are theoretically possible. So the research question for you is: can we extend minimax optimality results beyond standard sparsity assumptions to cover structured sparsity models with unknown structure and characterize the price of adaptation to unknown sparsity patterns. High dimensional inference constructs confidence intervals and tests hypotheses for individual parameters in high dimensional models, requiring debiasing or sample splitting techniques to account for selection bias and regularization shrinkage. Clinical trials evaluating drug effects while adjusting for thousands of genetic covariates use debiased lasso to construct valid confidence intervals for treatment effects, supporting regulatory approval decisions with rigorous uncertainty quantification. How can we develop simultaneous inference procedures that provide valid confidence bands for multiple parameters of interest while maintaining efficiency comparable to Oracle estimators that know the true sparsity pattern? Now, that's a question that you can ask. Computational statistical trade offs describe scenarios where statistically optimal estimators are computationally intractable, forcing practitioners to choose between statistical efficiency and computational feasibility, potentially accepting suboptimal rates for practical algorithm. Sparse inverse covariance estimation for 10,000 variables faces a trade-off where convex graphical lasso is fast but conservative, while exact subset selection is optimal but NP hard, leading to acceptance for approximate solutions. So, can we characterize sharp phase transitions between statistically and computationally optimal regimes? Identifying problem instances where polynomial time algorithms provably cannot achieve information theoretic limits under standard complexity assumptions. Emerging challenges. Future directions include developing methods for heterogeneous high dimensional data, transfer learning across related datasets, robustness to distribution shifts, and integration of deep learning with classical high dimensionality or high dimensional theory. So, once again, this is something that we bring in deep learning in this, and that's where machine learning kicks in pretty high. So, one major frontier is heterogeneity. Modern datasets often combine structured data, patients' demographics and health care, genetic variants, and life sciences, with unstructured data, medical images, clinical notes, each requiring different statistical approaches. Current methods often analyze each modality separately, but optimal inference requires joint modeling that respects each modality's structure while leveraging complementary information. Transfer learning, borrowing strengths across related datasets or tasks. So the precision medicine invariates, as I mentioned, combine genomics, proteomic, metabolomic, and imaging data from diverse platforms. So I suggest you to conduct research on these areas by applying the artificial intelligence, machine learning, and the high dimensional statistics. So let's continue in next lecture.